Hello, everyone, and welcome to this Chemistry World Nobel Prize Reactions webinar. I'm Mariana Kneppers, Chemistry World Science Media Producer. Today, we'll be talking all things Nobel and all things metal organic frameworks. We have a stellar panel of speakers today, and I'm very excited to introduce you to them. Today's webinar is very exciting, perhaps our biggest of the year, features a wide range of guests from across the world. We have speakers today from the UK, Norway, Australia, India, the US, and everyone's in different stages of consciousness and awakeness due to such a wide spread of time zones. So we massively appreciate them all taking the time to share their reactions and stories with us today. I will be speaking with each of them in turn, after which we'll open up the webinar as a wider discussion and take some questions from the audience. Now, we have a lot to fit in the next hour, so let's go ahead and jump right in. We'll start with Chemistry World's senior science correspondent, Jamie Durrani. Jamie reports on the latest chemistry breakthroughs, as well as areas like science policy that are of direct relevance to the research community. Jamie, if you could go ahead and come up on screen. There he is.
Hi, Mariana.
Hiya. Now, can you set the stage for us here? Who are this year's prize winners, and what are their stories? What are their backgrounds?
Yeah, absolutely. So, I'm sure most of the audience probably have heard by now, but three winners of this year's Nobel Prize in Chemistry. So I think we can see them on the screen at the moment, actually. So Susumu Kitagawa, who is based in Kyoto, in Japan. Richard Robson, who's based in Melbourne, Australia, and Omar Yaghi, who's at the University of California, Berkeley. And what they've been awarded the Nobel Prize for is their work developing, as you said, metal organic frameworks, which are these really famous porous materials made up of metal ions and organic linker molecules. And so, yeah, I can talk you through a little bit about what each of the three of this year's winners actually did. So I think
absolutely. Because from what I understand, Richard Robson was kind of the one who first came up with the ideation of these metal. Well, I think he termed them something different, didn't he? I think the metal organic coordination polymers is what he called them.
Exactly. Yeah. So he's spoken previously about how in the 1970s and 80s he'd been really inspired looking at like these old school wooden molecular models, in particular a model of the structure of diamond, which is this really famous network of carbon atoms. And he wondered, well, what would happen if you replaced each of the individual bonds with longer molecules? Could you make a similar repeating structure, but on a slightly larger scale? And so he'd been thinking about this for a long time, and then in the late 1980s, he actually sort of demonstrated this in practice. So in 1989, he published a paper in the Journal of the American Chemical Society, where what they did is they got these organic molecules that had like 4 arms, and on the end of each of these arms, there were nitrile groups, and the nitrile groups, each of those could coordinate to a copper ion. And they showed that just like with diamond, you got this really beautiful repeating structure. So at the time, they framed this an infinite polymeric framework. And that is really the kind of seminal moment for this field. But he, at the time, he kind of predicted that this was really a whole new class of material. Like, you could change the metals, you could change the organic molecules, and you could come up with many, many variants of these structures. And he also kind of realized that the gaps in between each of the individual units could have some pretty interesting applications. Like you could use those pores, those cavities, to do some interesting chemistry. So that was
Jamie, yeah, just because I think I'm going to bring in Petra now to just talk a bit more about those metal organic frameworks, but we'll come back to you in a bit if that's okay.
Yeah, sure.
Cheers. Thanks so much, Jamie. Now we're going to have a little chat with Petra here. Hi, Petra. She is a professor in porous materials at the University of Oslo, and she holds a PhD degree in chemistry and physics. And much of her work focuses on metal organic frameworks for energy and environmental applications. So Petra, thank you so much for joining us. Now, could you give us a bit more of a background of metal organic frameworks? Tell us a bit more of how the field has developed now. What are these, what do they even look like? What do we use them for? Yeah.
Yeah, thank you, Mariana, for the kind introduction and also for the invitation. I'm really privileged to be here. So first and foremost, I would like to start by saying that I'm a chemist, mostly, and I think MOFs are fun. And they're kind of the chemical Lego. And so you can use almost the whole periodic table of elements to assemble them. And also importantly, they're very modular materials. So they're built up of two major types of building blocks using both inorganic and organic chemistry. And there is a sort of controlled architectural element to their assembly, which means that parts of them can be interchanged. So that makes them very varied and very modular, as I say. And this is related to Omar Yaghi's work with the isoreticular chemistry. And I brought a little prop here because this is a model of a MOF which has been made. I don't know how you can see it. It is quite sunny still here in Norway, but maybe not as bright as I would have wanted. But so this is made by my colleague Petter Lillerud, who's the inventor of the UIO MOFs, and he's also a very keen modeler. So you can see that these bits here, perhaps I can hold it like this, that these blocks, these are the inorganic nodes. So here are these are zirconium oxide-like clusters, and there are these organic linkers that interconnect the nodes. And what's also very important that when these blocks self-assemble, they kind of build up this three-dimensional crystalline and also highly porous structure. And these pores are open, so as you can see through those, so they're interconnected. So which means that things can flow through them. And this is actually very important for applications. And then there are several possible definitions of what MOF is, but I think this type of the porosity and the crystallinity is very important because that distinguishes them from previous coordination polymers, such as, for example, Prussian blue, which have been around for a long time. And this kind of modularity also enables them that you can put, for example, organic groups on the linkers, so you can make them very functional, and you can have several functionalities then in the same time. And because they're so porous, they're actually practically all surface. And also, of course, the wall or the surfaces can be chemically fine-tuned. So in my opinion, perhaps the most interesting part, first and foremost, is the void space in it, and of course the wall of it. But also, their perhaps most interesting properties arise from interactions with guests, be it molecules or ions that go in there. And so this also gives rise to many of the potential applications they can have. So, for example, and mostly, we can tune the interactions with these guest particles. So this can give rise to chemical reactions, so we can use them as catalysts, but also we can, once again, by tuning the interaction, we can use them for gas separation or gas storage or even capture, as for example, Omar Yaghi's, I think it was mentioned that the moisture capture from air in the Nobel description. And also, of course, there can be this kind of physical element to it. And I think one more important thing is that it's not just the gas molecules that can be affected by the MOF, or the gas molecules that can be affected by the MOF themselves, but also the MOFs can respond to the interactions with the gas molecules. And I think this is another important potential application in which, for example, for sensors, and this is hugely related to Susumu Kitagawa's work with the flexible frameworks.
It's amazing. So they are very, very customizable systems, aren't they? Thank you so much for that kind of very whistle-stop tour through MOFs. We'll come back to you in the kind of general Q&A near the end, but I'm going to go ahead and pass along to Stuart now. Stuart is somebody who has been working with, or who worked with Professor Robson in the very early days of metal organic frameworks. Stuart completed his PhD in his lab in 1986 at the University of Melbourne. Now he is a professor at Monash University, and his research focus is mainly in the areas of crystal engineering, coordination polymers and MOFs, supramolecular chemistry, inorganic chemistry, and chemical crystallography. He's got lots of specialties, very multi-talented person. Thank you so much for joining us today, Stuart. As kind of a PhD student in the early days, did you realize the significance of this field at the time? Did you have any idea it was going to grow to be something so massive?
No, not at all. Clearly Richard did, so you can go back to his original paper, and so much of what is important in the field is in that paper. But personally, as a student, I was just trying to keep up with the ideas that Richard was generating, and following his lead and suggestions. But also in the early days, it was a question of learning to walk before you could run. And so we were not so much focused on applications, but just would the idea work? And so could we take different metals and linkers and target particular topologies, and if we did, what would our hit rate be for that topology as opposed to something else? Or would we even get nets, or even would we get crystals? And so it was really trying to work out, is this feasible, and what's the sort of things that we get? And so every structure was a surprise, even if it gave you the predicted net, that would be a surprise. And then there was all sorts of things that we came across in terms of interpenetration, in terms of new network topologies that we hadn't thought of. So it was very exploratory at the time.
Gosh, I can imagine. I mean, what kind of got you interested in the field? What brought you to Professor Robson's lab?
Oh, well, there's a story in that. So Richard, before he created coordination polymers, he was famous for what are now called Robson macrocycles. And I was originally came to do that, and Richard said, "Oh, I have this other project that I'm just trying to get some students on. Would you be interested to that?" And my reaction was, "Yeah, sure." But and I'm pretty glad he suggested that. But
I was going to say, quite a good pivot.
Yeah, it's probably a good call in hindsight. And once we started, I mean, seeing some of these structures are just gorgeous. They're just beautiful structures. And we get a little bit, I think everybody's used to seeing them now, but in those days, it was the first ones that were being made. No one had ever seen these sorts of beautiful architectures on the sort of scale that we were doing. And so sort of after a while, I kind of go, oh, okay, this is a little bit special, and this is kind of cool. And then you sort of think, oh, this is a little bit of a guilty secret, and why is nobody else doing this, and have I missed something that no one else has got onto this idea? I mean, this is typical of Richard. It's just his whole career is about brilliant ideas that as soon as you say them out loud or he demonstrates it, you go, oh, of course, and why did nobody else think of that before? So, but if you'd have said to me now what the field is now, it just would have blown my mind. So one of the big privileges and things that I will take to my last days is just being able to be at the start of a new field of chemistry being created, and then just watch it blossom and explode, is from a front row seat is something that I will treasure forever.
Gosh, that is amazing. I mean, it's like you say, not many people have that privilege, so what a, it's right place, right time, isn't it?
Absolutely.
Kind of is what it is, isn't it? But we actually have another member of kind of that research collaboration group with us here today. So I'm going to call on Brendan Abrams to come on screen. Brendan is also joining from the early hours of Australia. Thank you so much for being awake and being with us. He's a chemistry lecturer at the University of Melbourne, and he's been working with Robson since 1984. Hi, Brendan, welcome.
Hi, Mariana, how are you going?
Yeah, good, thanks. Probably a bit more awake than you, I hate to say, but you look great, though. I mean, for being up at...
You're the only person who said that today, so...
Oh, well, you have kept in close collaboration with Professor Robson since kind of the early years. So you've also had quite a unique perspective of a front seat, kind of as Stuart was saying, to see the field develop over time. What changes have you seen? I mean, have the changes surprised you?
Oh, yeah, I just could never have predicted, just the way things have worked out. But we actually started in 1989 with Richard, and I had a mentor at the time, Bernard Hoskins, and he was a wonderful man, a brilliant crystallographer. He worked with Dorothy Hodgkin, who did a postdoc with her there, who won the Nobel Prize in 1964, and he was a crystallographer. And so this combination of Richard Robson who's making these compounds and Bernard Hoskins, who was doing the structures, was a really complementary collaboration, and they worked together so well. And Bernard said to me in 1989, I just finished my PhD, and he said, oh, Richard's looking for someone to do some structures. And I said, oh, I'll help him out. That would be happy to help him out, determine a few structures. And Stuart joined the lab at the same time, and it was a really exciting time, because when Richard told me about his ideas, I thought, wow, this is really fantastic. And I went home and told my dad, and I said, Dad, this guy's come up with these wonderful ideas. And he said, oh, you should work with him. He sounds like he's a really bright guy. So
get involved.
So I moved away from a tutoring position and became Richard's postdoc for, I suppose, 14 years until I had an academic position. But they were very exciting times. I think early days we had a very strong emphasis on topology. And there was a British structural chemist, A.F. Wells, and Alexander Wells, and he was a brilliant man. I think he wrote Structural Inorganic Chemistry, which is like a Bible, a very thick book, and all inorganic structural chemists use this book. But he had a strong emphasis on topology, and he wrote 2 books in the late 70s, and that was really like a roadmap for us on which way, how do we link things together, or how do we understand the connectivity of networks. And that provided a way of not only describing these nets, but also making predictions about what sort of networks might we be able to expect. So that was a really useful thing. Probably that sort of emphasis has now changed, because I see that the change towards more, rather than discovering new nets, it's the applications which are really important. I think that's just the evolution of the field. It's a really important part. And speaking before about UIO 66, and I think I'll look at that and think, wow, what a fantastic structure that is. It's really impressive. But I guess in those early days, we had ligands which were nitrile and pyridol based. And I think we began to understand very early on that you needed reversibility when you were making these things. So the molecules would come on, they needed to come off if they connected in the wrong way. So you needed that reversibility, and weaker coordinate bonds were well suited to that. But the problem was that if they lost solvent, they perhaps were not as robust. And so people said, well, how can we make it a stronger interaction? And they started to use charged donor ions, or the chelate effect. And that produced more robust materials. And that's led to, applications. I think that's probably one area. Probably a big change in development in the area occurred with the way crystallography changed too. In the early days, you'd measure one reflection at a time. Data collections could take a week. To solve a structure could take a long time. nowadays you can do it in 10 minutes.
It's amazing how fast technology changes things. Yeah, it's fascinating, isn't it?
Yeah. So that just allowed us to, we've seen that change. What took us, 2 months early on now became, a really, really short job. Yeah, so that's been fantastic to see that development. But that's what amazing. It means is that the crystallographer was a highly specialised scientist, and now anybody with half an hour training can determine a structure.
It's just changed so much, hasn't it? I mean, speaking of, I'm going to switch gears now, actually, Brendan. We'll come back to you in a couple of minutes. Thank you so much. Cool. Speaking of kind of developments when it came to metal organic frameworks, I'm going to bring in Sujit Ghosh, who actually worked with one of our other Nobel Prize winners, Professor Kitagawa, as a postdoc in 2009. Sujit currently focuses on the development of metal organic frameworks and related advanced functional porous materials for clean energy, sustainable environment, and safe drinking water. Really lovely to hear from you. Thank you so much for being on here. So by the time that you joined Professor Kitagawa's lab, metal organic frameworks were already quite established at this point. So what made you decide to join Professor Kitagawa's lab? Was there something particular going on with metal organic frameworks that you were interested in getting involved in?
Right. So I'll maybe put 4 points why I joined this lab. First of all, it was of course, he was one of the few big stars that time on compounds is very still early stage. And particularly, he's one of the Anglo-Chem review paper. Still, it is one of the highest, most cited paper. It is more than 12,000, I guess now. So that was very famous. So that compound also, it was the way it was written very easy, and that particularly here emphasized on flexible MOF compounds. That attracted me, and I wanted to work on that flexible MOF compound, which also was highlighted during this prize ceremony. As you saw that how solid state structure change, that was very fascinating for me. And I wanted to work on that field, and luckily I could contribute on that field. And still, what we did, let's say, we made this kind of flexible behavior, 2D material from 2D to 3D, and again 2D back. I could make by single crystal to single crystal transformation, and that kind of examples literature still very rare. So only I remember after that immediately within our year or so from Kitagawa's group only someone published, and that also there very special trick was that what we could do. We got as a single crystal machine as a kind of toy. We could play day and night with that instrument, and then even we never knew that even we can collect single crystal at 100 degrees centigrade, because that was possible because of that. Even literature, very few reports are there. You can collect data at that temperature. We had to do because only that temperature it was possible to get in 3D. Otherwise, it was room temperature is not possible. So that kind of things we could do, flexible behavior of MOF compound. This is really special, and that was the reason I also joined there, or I wanted to work on that field. Third one is one thing I like that time, that I thought that kind of freedom of research. I used to see that from Kitagawa's group, we used to see different kind of research rather than that way you could say Professor Yaghi was developing one systematically, very systematically, but Kitagawa's group I found that is very flexible. That I thought that probably this group I will have more freedom. I can work on different ideas. Something is not clicking, that's something over, because that time we are afraid also if something is not working, what will happen. So that was the also I was relaxed that okay, here I can probably contribute. And third thing also, honestly, this is fourth one is I saw that if you see total number of group members and number of papers are coming, it was Kitagawa's group was good, score was good. So I thought that if I go, probably I can at least get some paper, my career will be safe. Exactly. That way, Professor Yaghi's group, you say that time he had big groups, but I saw only very papers coming, but very few. Then I thought, okay, either I'll make it or break it very probably, so that it may be risky very. So that kind of thoughts came to my mind, and lastly, actually I got chance in Professor Kitagawa's group accidentally, you can say. So in USA and Europe, they allowed to join as a postdoc before even PhD degree. but Japan, they don't allow. And Professor Kitagawa didn't know. So I wrote him even before like getting my degree, just before defense. So then I wrote, and then when I reached there, he said that you don't have degree. So no, I said no, I just submitted yet to get degree. He said, oh, this is like degrees. Japan is like license, without like driving license. Without license, you cannot drive. So you cannot do postdoc without degree. Then I came back and then got degree, of course, like short time. So that was also kind of accidentally I could reach. Otherwise, probably I would have missed that chance. So that was the kind of.
Oh, that's amazing! Gosh, yeah. I mean, again, another situation, kind of. Well, in this place, right place, maybe wrong time. Had to come back and do it again. That is amazing. Wow, a really, really interesting perspective. Thank you so much, Sujit. We'll come back to you once we've opened up the panel again, but very much appreciate that. What an interesting story. So one of the biggest topics for discussion around metal organic frameworks is their potential for use in sustainable development. So here to shed more light on this is Diana D'Alessandro. Diana is the director of the Net Zero Institute at the University of Sydney. She is also a professor in chemical and biomolecular engineering, focusing on functional materials for applications such as greenhouse gas capture, catalysis, and energy. Hi, Diana, how are you?
Hi, Mariana. Thanks for having me.
Yeah, thanks for being here. Another early morning for you as well, I suppose. But hopefully the excitement is. Yeah, it's just becoming normal these nights.
That's it.
So my question to you is, how can these metal organic frameworks be used in sustainable development? There's been a lot of talk about how they're being applied to reach sustainability goals. What applications exist at the moment?
I think a number of colleagues have already touched on this, and I think the very famous UAO 66 has been touched on a couple of times, but there's another very famous framework called MOF5. And so, Richard, Robson and Stuart and Brendan have touched on this beautifully, foresaw the opportunity in using that void space, and Petra, touched on the essentially the being the architect, if you like, inside the void space and being able to modify the chemical functionality and the shape and the form and the catalytic properties. And so this quite famous MOF5, which had the robustness that was needed for these MOF materials to be ones that could be, sufficiently robust to be potentially useful in industry, was an important framework because it was shown that it could store hydrogen, and that was one of the very early sort of demonstrations of hydrogen storage in a material, which of course was politically important at the time, for example, in the United States, in terms of, potentially the advent of hydrogen-powered cars and being able to actually, how could you actually store that hydrogen and do so in a safe manner? And MOFs was, a great potential solution to that. From that point, we've seen a lot of other applications, such as carbon capture and storage. So the notion that these MOF materials could actually clean up effluent streams from, for example, major point sources of greenhouse gases like coal-fired power stations, or even cleaning up natural gas. From there, we've sort of seen this incredible, evolution into all manner of different types of separations. So I think Petra already touched on the water purification and harvesting. So you can envisage, using these materials in very arid, dry climates where there's water scarcity, and being able to actually essentially take moisture out of thin air. Not only that, you can take carbon dioxide and other greenhouse gases out of thin air. And I think Petra also touched on that aspect of catalysis, being able to put molecular catalysts, but do that inside the structure of the MOF, which means that, you can actually get chemical reactions happening that are totally different to what would happen in a liquid solution or any other solid material. And I mean, that's just the tip of the iceberg, which is, we could go on for hours. Environmental sensing and monitoring. We're starting to see now the advent of, circularity of MOFs. So actually taking waste resources and being able to recover components of those waste resources and then make them into MOFs. So we're starting to see this aspect of real sustainable production. And even then, using MOFs for water splitting. So not only can you capture the hydrogen, but you can actually split the water that produces the hydrogen. You know, medical imaging, medical applications, you know, it really is a very rich opportunity. But of course, with all of this, there are challenges. And so I think we all acknowledge that scaling these materials, making sure that they're economically viable, making sure that they're safe, and how do we actually integrate the materials into real engineered systems to be useful in the real world? You know, these are just some of the challenges now that engineers are really trying to tackle in order to take the science from the lab bench and actually make sure that we see the incredible potential of these materials play out in the real world and have the impact that we need to address some of these major global problems.
Yeah, it's really excellent segue that you've mentioned scalability, because our next guest is involved with the commercialization of MOFs. So I'll say thank you now to you, Diana. Thank you so much for that. And we'll bring on Will Morris. Hi, Will. How are you? Will is he works at NUMAT. He is he's the director of business development, at NUMAT. And is heavily involved in the commercialization of MOFs. He completed his PhD under our third Nobel Prize winner, Professor Yaghi, in 2012. And NUMAT is a company that focuses on, as I said, the commercialization of metal organic frameworks. Will, what is the most exciting thing about this, commercialization of these? Because we're learning about all these aspects. That it's something that can be applied in a number of subject areas, has massive potential. What is the most exciting thing about being able to work at the forefront of this commercialization?
So for me, working at the forefront of this commercialization, it's been taking that work that I did in an academic lab, in Professor Yaghi's lab, and kind of turning that into reality. Like, ultimately, how do you take all of these exciting applications that we have for MOFs and, turn that into commercial products? And the last speaker did a great job of talking to some of those challenges. Like, you're talking about the scalability of these materials, right? Like, how do you go from making a gram of those materials to making tons that you might require for a commercial product? And then how do you integrate it forward into a product as well? Like, how do you get it in the right form factors and all of the challenges there? And then there's often unsung challenges that you have to think about, like compliance, like regulatory, safety as well. Like, how do you safely produce these materials at scale? They're fascinating questions that at NUMAT we've been tackling for about 10 years now as a small company. And we are you need a very multidisciplinary team, I'll say. Like, I'm a chemist by training, but we have chemical engineers, we have a business development team, right? Like, you have to make sure there's a customer for your product at the end of all of the hard work that you're doing. These are the challenges that sort of NUMAT has been tackling, and we launched the first commercial product in MOFs called INX in 2016, which is, honestly, it's not the applications that you hear about, water harvesting or carbon capture, that would require very large amounts of MOF. It's a safety product that enables toxic gases to be stored safely. It's a high value product that requires relatively small amounts of MOF. Now we're scaling for applications in chemical protection that don't require PFAS, and that's work that we're doing with the Department of Defense. And we're also focused on applications in industrial decarbonization. Now, another thing that gets me really excited about this field is, we started back in 2013 and there was probably a handful of MOF companies, but now there's, 50 to 100 MOF companies globally working on all of these wide range of applications, sort of tackling these challenges, bringing them forward, water harvesting, carbon capture. There's a big push in AI machine learning, not to be surprised really at the moment. Materials discovery. So the field in sort of commercialization of MOFs has grown, exponentially from the early days. So that's very cool.
Yeah, it is incredible to see just how much it's grown. And I imagine, a lot of these Nobel Prize winners, the three are just kind of looking at how the future has, what the future is of these materials, and it's fascinating to see the commercialization and the potential for it moving forward. I'm going to take this time now to invite everyone back on screen so we can go ahead and open this up as kind of a larger panel and take some questions from the audience. Here we go, slowly trickling back in. Now, I am going to go ahead and start with this question from the audience. The 3 winners were given an equal share of the prize. How do they each contribute differently to this field? Jamie, you were kind of beginning that discussion. Do you want to go ahead and pick that up again? If I had cut you off there.
Yeah, no, of course. Yeah, I think like obviously at the very beginning of this webinar, I talked mainly about what Richard Robson was doing in the kind of late 1980s, this sort of, and he was really recognized for this initial realization of how you could go about making a MOF and their sort of early potential, and coming up with this first deliberate design of one of these repeating framework structures. Yaghi and Kitagawa, I mean, they've obviously contributed massively to the field, but I think the Nobel Committee particularly were recognizing them for, I mean, really taking the idea and running with it. They came, I mean, we've talked about some of these already through the webinar, but they had some real milestone papers in the 1990s and early 2000s that really helped to define the field and demonstrate how these materials could be used. I mean, Yaghi literally, you could argue, literally defined the field in that he coined the term metal organic framework, and he also came up with the term reticular chemistry to describe the sort of rational design of these materials and how you can kind of tinker with the linker molecules and come up with all sorts of different shapes and sizes of the cavities that we get in these MOF materials. But apart from just catchy names, another really important thing that Yaghi did in 1999, and which I think Diana mentioned earlier, was he published this paper on MOF5, which was that they were able to show that it had this huge internal surface area. Like I think a couple of grams of MOF5 has a surface area the size of a football pitch. And this was like an order of magnitude higher than what had been seen in other porous materials like zeolites. So that was really important for capturing people's imagination and making them realize, how useful these materials really could become. And Kitagawa also, had some really important milestone papers around that same time. So he had a paper in Angevin Chemie in 1997, where he developed these MOFs with these internal channels that ran through them. And he was able to show that these could absorb and release gases like methane, nitrogen, oxygen. So again, showing like an early, real practical function of these materials. And he also, the Nobel Committee also pointed out that he kind of realized that the MOF framework itself didn't have to be completely rigid. And he developed the idea of these flexible MOFs where the framework could kind of expand or slightly change in shape when it took in a guest molecule. And he kind of pointed out that property itself could open up the materials to all sorts of different functions where they could work, and their behavior could be controlled using external stimuli. So things like light and pressure could be used to manipulate the MOFs and how they work. So those are some of the kind of key things that these guys did.
Yeah, it's quite a magical material. And what really struck me about the Nobel Prize announcement was they kept describing it like Hermione's handbag in Harry Potter, because it does have that sense of magic to it, doesn't it? It just, to have as much surface area as the size of a football pitch. I mean, how does that even happen? It's really hard for the mind to wrap around that concept, but these things do exist, and it's science and it's real, and it's amazing, these applications. Kind of off of that, given how incredible this material is and this discovery is, I'm going to posit this to the whole panel, but do you feel that now is the right time? You know, moths have been predicted to win for a few years now. Do you think that the prize is overdue, maybe? Do you think it should have been recognized earlier in time?
I guess I'll say we've been talking about this as alumni from the Yaghi lab since 2010. So I think in that context, we weren't too surprised. And if you see the predictions as well, it's been high on the list for a long period of time.
Yeah, I mean, Stuart, you were there from the beginning. Stuart and Brendan, is this something that you ever foresaw receiving a Nobel Prize? Is this over the years? You kind of saw all of the developments. I mean, have you just been waiting? Has it been like 10 years time? You're like, well, when is it going to happen?
Yeah, to a certain extent. I mean, obviously not in the early days. I mean, that would have been just crazy talk. But certainly in the last few years, certainly I've been nervously watching each year and with fingers crossed. I think it is a little overdue, but I'm happy it's here. And I think some of the criticism of MOFs was it needed to wait for applications and things like that, which always irked me a little bit, because the prize to me is not about is it going to give you the next widget? It's about, have you advanced understanding of chemistry and created something that our understanding that wasn't there. And I think MOFs passed that bar many years ago. And you look back at some of the prizes, some of the things like organometallic chemistry took 40 years before there was an application, but it was still a prize-worthy thing. So I'm very, very pleased it's finally here.
I can imagine. Brendan, how about you? Similar sentiments?
Yeah, I think Stuart summed that up really well, actually. That's I had the feeling, I wish I'd said that. No, that was exactly spot on.
Yeah, it is amazing, but better late than never, I suppose. I mean, it just, it's I actually haven't known much about MOFs myself, and it's been such a joy this week to kind of learn about them and see. It just gives you a bit of excitement. I think, Deanna, you had said earlier, there's a lot of bad news in the world at the moment, but this just feels like such a bright kind of headline, all of the potential that there is out there for this material.
I think so. And I mean, we have so many countries represented here online. I'm sure in terms of the listeners, they're probably joining us from many, many more countries. And I think we all know that the world is in a challenged place at the moment. Misinformation is rife. And I could certainly say for our position here in Australia, it is a challenge at the moment. We have a major review of our research system underway in Australia, and we're awaiting the results of that early in the new year. We also have a major review of governance in our universities, which is in question. And we have, a variety of other associated problems with productivity and so forth. And so I think the value of science is being questioned, the value of research is being questioned. And in a globe, in a time where negativity seems to be rife, it's so critical that we really do speak up for the value of knowledge and knowledge sharing and the passing down of knowledge through the generations that has inspired all of us to be people who are evidence-based and really want to ensure that we're, coming with the facts. So it's more important than ever that this be really cherished and be made visible. So thank you for doing this this evening.
Yeah, absolutely. I mean, I think, we at Chemistry World definitely share that sentiment. It's the importance of having, having scientific veracity and kind of sticking to those ideals. Absolutely. In a similar vein, oh, sorry, go ahead. Yes.
Oh, yeah, just to bounce off that and on a more personal level. So certainly within Australia, it's a small but very tight community of MOF chemists, which is now across a couple of generations, and to us, Richard is obviously the father figure, and just the joy, the absolute sheer joy within the community, particularly at times where it's a challenge, has been fantastic this week. It's just been a real pleasure.
It's so nice to hear about. Yeah, I think we had seen some videos coming through from the media team at the University of Melbourne, and there was one in particular that I'm not sure if it's been shared on social media or anything, but of Richard describing how he had received the news, and I think he was cooking fish at the time, and he kind of, he took the call and was like, "Oh, this is amazing," and he answers the question. He ends it saying, "And then I finished my fish. It was a bit cold, but." Then I went to wash the dishes, and that was that.
And if anything sums Richard up, that is it.
Honestly, that video just it filled me with a sense of joy, because you tend to see Nobel Prize winners as, these larger than life figures, very kind of respected figures within the community. But at the end of the day, they are just people, and you just are in the middle of eating fish one day and your life changes. I mean, it is a really, really incredible story. In that vein, we have somebody from the audience who's asking, in your experience, feel free, anybody, what personal qualities do you believe make someone a truly great researcher beyond intelligence or technical skills? Sujit, is that something that you want to answer? We haven't heard from you as much yet.
Okay, so what I say to my students, also that particularly research nowadays, what is that you are hardworking, it is not much of demand. So rather you should work smartly, and then that's what you read more and then plan better. That is the way of good researcher, I think. So before go to the bench, you should spend more time in the planning and read literature and see. You should know that field better than anyone else, better than me. So if I discuss anything, first time I tell, okay, work on this field. Next time I talk to him, I say, I expect I expect that you should talk more than me. So that means you read more. So that is, I think, one thing is important for researchers. So they should know the background before starting research. So that, I think, helps researchers to do very quality research. So that is my opinion, and I also felt that thing.
Yeah, and I think it's very important to kind of have those ideals, isn't it? Petra, do you, in your experience kind of working in this field, do you have any advice on, what makes a good researcher?
Maybe not advice, but I can say that I was, a few years ago, I was lucky enough to have one of these Japan Society for the Promotion of Science fellowships and or visiting professorships. And as part of that, I could visit Susumu Kitagawa's lab. And so because you meet these fantastic researchers at conferences, but you don't necessarily get to have in-depth conversations with them. And he's a fantastic and humble person, and he's very approachable. And I think these are very important qualities in scientists. And for two reasons, I suppose. On the one hand, science is so much greater than any of us. So I think everyone should see that and acknowledge that. And I think if you don't, then you probably don't appreciate science enough. And I think many of us, or them, I don't necessarily count myself among these greatest scientists, but so they are role models to some extent, at least to the students of us. And I think it's important what they learn and to appreciate that one day they might also get into this role and so transfer this kind of attitude as well. I think is very important.
Yeah,
I think one of the things I learned from Professor Yaghi that was really important for my career was how to effectively communicate your science, right? And that was how to give an effective presentation and how to write a scientific paper. And I'd say that's vital for any young researcher. But that's also gone over into my career. They're the most important skills that I actually learn in my PhD, because now I'm thinking about how I communicate effectively across a multidisciplinary team about what's important about the science that we're doing. So you have to be great at the bench and do fascinating chemistry, but I think it's also important, and it's definitely something I didn't think about until I joined Omar's lab.
Yeah, it is a massively important thing, isn't it? It's one thing to be able to do the science and be good at the bench, as you say, but to be able to explain the significance of these findings or the importance of, something like this, an award like this, or in order to get people to come on board and support your, you know, endeavors, you do have to be able to communicate it. And it's a language like anything else. You know, you do have to become multilingual, don't you? So yeah, it's something that I definitely believe in quite a bit, is, you know, the importance of science communication to bring people within to the scientific community. I'm going to switch gears and go a bit more technical now. We have a couple technical questions from the audience. How are metal organic frameworks modified for different applications? Can the porosity also be modified? I'm not quite sure who's best posited to answer that question, so I'm going to let whoever pop up and decide, but it sounds like quite a technical one.
Yeah, I can answer a little, but can you just also repeat the questions? I just missed the whole.
Yeah. So how are metal organic frameworks modified for different applications, and can the porosity also be modified?
Yeah. So this is well established now. So a few things I'd like to add here, that now this MOF materials nowadays, as you can see, even all researchers nowadays, people don't make any more MOF compounds. Now we will modify MOF compounds. So basically it's called post-synthetic modification. PSM. So that is like so MOF compounds are once like now a lot of more than 100,000 MOFs are there, and all of you know that there are a few compounds which is very well-known compounds and very stable, so we can easily modify. We can almost do like organic reactions. So that way, like is modification of MOF is not easy, like not very easy in that sense. And even same MOF compound now we can see plenty of application, because almost like some of the MOF, depending upon requirement, we can modify it accordingly for different applications. Okay, so in this regard, I would like to remind one thing, and particularly all of you, I would like to remind regarding Professor Jared Ferre. I think all we should miss him, and then he was one of the, I think, like early, and then one of the meal series particularly what came to my mind. Because meal series are one of the most stable compounds, and then probably he was one of the strong contender for Nobel also. And then of course I'm very happy that Professor Robson also he got, because he was one of the who started this research. But then I think it job became easier for Nobel committee, because would have alive, I don't know, like among them 4 them, because it can go to maximum 3 people, right? Like I don't know, like how they would have make it. So this kind of compound, like he contributed the meal series, particularly those who know like meal 101 or this compound, or like one compound, probably all applications you can think. It's so stable compound, and depending on requirement, we can modify like kind of different application. So it's not very difficult nowadays here.
Yeah. I think Petra's having her hand raised very politely. Petra, did you want to add on to that?
Yes, I just want to bring back my model, because I think this is maybe for some, maybe it's still not very visible, but maybe this is a relatively easy way of seeing how the pore size can be easily tuned. And this is also through the isoreticular chemistry that has been shown, or that I mentioned a few times before. So what you can see here, for example, is that once again, these are the inorganic nodes, and in between you have the organic linkers. And these linkers, maybe this is a better view here. So in this case, they're made up of 2 rings, but this can be just 1 ring, but it can be 3 rings, or sometimes more, but not an infinite number of them. And by tuning the size of the length of these linkers, so long as the node remains the same, you can typically modulate the pore size. So that is one of the earliest ways of tuning the pore dimensions. And another way is once again through coordination chemistry. So by changing, and I think this is what Sujit has touched upon as well. So in this example, these are zirconium 4 ions and oxide ions around them, but you can exchange them, for example, in the MOF5, it would be zinc, and they have different coordination chemistries, and therefore they have a different environment around these inorganic nodes, which lend themselves into different pore sizes as well. So the pore dimensions are very tightly controlled within MOF chemistry.
I see. Very, very customizable. We have a follow-up from Ju Yi. Can metal organic frameworks be functionalized to interact specifically with biological molecules like proteins or DNA, or maybe in any other practical medical application? Now, I think I've seen things online about recent developments in using almost edible moths that kind of go on the outside of things like acetaminophen and stuff like that. I'm not sure if that's the same thing, but Petra, it seems like you have a hand raised. Do you have an answer for this one?
Yeah, I didn't leave it on. I put it on again. But yeah, so I think I briefly mentioned, but also the animal cursor mentioned earlier that this sort of interaction between the porous structure and the interface at the surface of the moths and gas molecules is one of the most important properties or potential ways to applications that moths have to offer. And I think one of the most important areas in which moths can be used aside of energy research is healthcare and medical research. There has been a lot of work on using moths as drug carriers because you can fine-tune the interaction between the drugs and the loaded drug molecules inside the pores. And then so you can make sure that they're only delivered in the parts of the body where that particular drug is to be used. I think it is possible to fine-tune the outer surface as well to interact with biological molecules, but I would like to say that the pores of the moths are typically not on the same size level as biological molecules often are. So it's more like in the outside of a moth particle that they would be able to interact.
I see. Does anyone else have anything to contribute on that?
Okay, please go ahead.
Yeah, there's definitely been some interesting work on biological applications of moths. Like I think of one example from Omar Farhar's lab where they're looking at insulin delivery and showing that you can do that without the need of a needle. I will say there's also several companies working on the biological applications of moths as drug delivery, agents and contrast agents as well. And some of those moths are in sort of later stage clinical trials as well. So there has been progress both at the lab scale and also as you progress through to commercialization.
Yeah, I'd imagine things like they would be quite useful for things like cancer, where you have to deliver those quite targeted treatments to places, and you can kind of customize it to almost target certain areas. I could be completely making that up, but just that's kind of, is that something that has been developed?
Yeah, so some of those contrast agents or anti-cancer drugs have been delivered literally as part of the moth, or they've been added by post-modification as well. So it certainly is a new field, I would say, relative to some of the traditional moth applications. And there's still challenges like how do you make them colloidally stable so you can deliver them, and then you've got all the questions about medical trials as well. But people are making progress.
Yeah, I'm going to try and fit in one or two more questions in, just because we're slowly reaching the end of our time. We've had this question from the audience. What is the role of AI to help discover new metal organic frameworks and focus experimental efforts? Is that anything that, has anybody been using that within their lab recently?
So
go on.
I think it's a fascinating topic, AI and machine learning for material discovery. There's certainly a lot of ongoing efforts. There's been some big investments made in companies to do exactly this. We're seeing a little bit of this work at NUMAT, like we've had a collaboration with some large AI companies looking at their outputs. I think we really need to work on the data sets that we're collecting, like collect high quality data on these moth materials so we can train the AI, because otherwise you end up in a situation where if you've got bad data sets to start off with, they make bad predictions. So it's a relatively new field for moths, but progress is being made.
Yeah. And I'm going to fit in one more question. We always like to end on a bit of an advice question. So what advice would any of you give to young researchers entering the field of materials chemistry today, especially in light of the moths revolution? Maybe Brendan, do you want to have a go at that one?
Yeah, I'd say really enjoy it. I mean, I think as a young researcher, your time in the sun is really limited, and I think do the chemistry just for the enjoyment of doing the chemistry, of discovering new things, and I think that will give you a wonderful pleasure. And many of us won't have the opportunity later in life to do those sorts of things, work in a laboratory, make new compounds, and while you have the opportunity, make the most of it, because I think that's something you'll always cherish.
Yeah, anyone else? Deanna, do you have any specific advice?
Oh, I think that was so beautifully said, and it reminds me why I just love collaborating with colleagues like Brendan and Stuart and many others on the call here, because I think the real passion for the science, for discovery, for new knowledge, I think that really lies at the heart of it. That has to be the purpose. I mean, all of the bells and the whistles and the accolades, you know, yes, that may come afterwards, but fundamentally you have to enjoy what you're doing, and if you enjoy what you're doing and you're purpose-driven and passionate about that, then you'll show up every day, even when it's hard and even when you do the NMR and it really is not what you want to see, because there's lots of those days. So you've got to be in it for the right reasons.
Oh gosh, that is, I think, excellent advice, and something I, you know, would tell my younger self in my early kind of science career. I think it is just about enjoying it and making sure you have the passion for it, because passion is what will pull you through those very difficult times, isn't it? Oh, thank you so much, everyone. Unfortunately, that's all the time we have for today. I mean, we could probably do this for a whole other hour, but I think we should probably let some of you go to sleep and some of you go about your day. If you would like to learn more about this year's prize-winning chemistry, our friends at the Cambridge Crystallographic Data Centre are running a live webinar next week titled Frontiers in MOFs, Creating Real-World Solutions with MOFs. We'll put this link in the chat for you to find out more and register. I'd like to extend a huge thank you to every one of our panelists for joining us today. Your input has been very valuable, and it's been lovely to hear all of your stories that you have about this year's winners. I'd also like to thank my wonderful Chemistry World digital team, Chris Pink and Ben Vausler, who have been working hard behind the scenes to make sure everything's running smoothly and that we all look and sound fantastic. And a thank you to Jamie as well, who has joined us from the Chemistry World team to give his input. Thanks again, all of you, for joining us, and we hope to see you in another Chemistry World webinar soon. I'm Mariana Kneppers, Chemistry World Science Media Producer. Goodbye, and see you next time.
Thank you, Mariana. Thank you again.
Thank you, Mariana.